Okay, so here we go with the second video lecture, continuing to talk about pharmacokinetics. I know there's been a lot of material right now, and there'll continue to be quite a bit of material, but I ask that you trust the process, that I'm guiding you along as slowly as I can, and that in time it'll all kind of add up and turn into a cohesive idea. You guys are going to get really good at this stuff. It's going to be good. During the second unit is when you'll have a chance to sort of start flexing these muscles as we move into talking about addiction. And this will allow you to continue to sharpen your understanding of this early material. So I don't expect you to get it all at once, but in reality, the difference between an A and a C in this first unit is how much of all this material you're able to absorb really quickly. But you will have the opportunity to kind of apply it later on. So we've been talking about pharmacokinetics. Remember that the pharmacokinetics are the factors in drugs in the body that influence, how the drug ultimately affects behavior. And so far, we've talked about routes of administration, absorption, and binding, and these are all pertinent in terms of how the drug gets to the brain to begin with. That being said, the route of administration encompasses everything. But talking about biotransformation, biotransformation is the process by which the chemical structure of a drug is changed, which then changes its effect in the body. And this is really important, this concept of structure-function relationships. So this is going to be a really important function in understanding how drugs work in the body and the brain now, but also throughout the course. I mean, so much of how the brain works is reliant upon this idea of the structure of a molecule, the structure of a receptor, the structure of the brain governing how it functions. And, we've seen the importance of this structure-function relationship in the difference between pseudoephedrine and methamphetamine, in that, simply the hydrolysis of a hydroxy group from that pseudoephedrine creates a molecule in methamphetamine that, has a much different function. So the structure changes how the drug gets to the brain. And as we move along, we'll also see how the structure of a drug affects how it binds to active sites in the brain. So biotransformation is merely the process of transforming a molecule into another molecule, such as transforming heroin into 6-acetyl-morphine and then turning that into morphine. Biotransformation can occur by natural chemical processes such as oxidation or via chemicals in the body with specific purposes in transforming drugs. And these are called enzymes. So that, again, as you see these words in red, these are going to be key terms. And we'll discuss the synthesis portion of biotransformation later, but right now we'll really be focusing on the inactivation and degradation of drugs. So enzymes are merely chemicals that facilitate changes in molecules. Enzymes can be identified by the suffix "ase". So for example, alcohol dehydrogenase is an enzyme that breaks down alcohol, and 5-hydroxytryptophan decarboxylase transforms tyrosine into 5-HTP. So I'm going to insert a question here. So here we have two examples of biotransformation by enzymes. So let's see if I can pull this up. Oops. Sorry. Okay, so I think this was how it worked before, but okay, so here we have what I was saying, alcohol dehydrogenase. And that's the enzyme that turns ethanol into acetaldehyde. So that's a degradation process. Ethanol is being broken down into acetaldehyde. On the other hand, as I mentioned, tryptophan hydroxylase is synthesizing tryptophan into 5-hydroxytryptophan or 5-HTP. And then it's another enzyme that turns that 5-HTP ultimately into serotonin. So again, biotransformation is either the breakdown or the synthesis of molecules. So enzymes are chemicals in the body that facilitate changes in biomaterials. They can degrade materials or they can synthesize materials. But as I mentioned, we're going to specifically talk about degradation. So the process of chemical degradation in the body is called metabolism. And metabolism occurs in many tissues, most tissues, including the brain, but the primary site of drug metabolism is in the liver. And metabolism kind of breaks into two different phases. These are called phase 1 and phase 2. So phase 1 metabolism, also known as non-synthetic metabolism, consists of these, I think these are just three of several phase 1 forms of metabolism. And the non-synthetic basically means that it doesn't require another molecule to metabolize the substrate. So there's no other molecule that you need to add anything on. These are naturally occurring reactions or enzyme facilitated reactions that are merely removing a hydroxy group or adding a hydroxy group. They're very just chemical changes in the molecule. Whereas phase 2 metabolism is called synthetic metabolism, and it requires another molecule to conjugate a new molecule. Wish I had a better example of that. But typically metabolism will create a less lipid-soluble molecule, meaning that this new molecule, or a metabolite, is more restricted to water. It's not going to be absorbed into the blood or absorbed into other tissues, and that allows it to be excreted. So when chemicals are degraded or metabolized, they become these secondary chemicals called metabolites. So, for example here, well, I'm going to insert a question. So again, when chemicals are degraded or metabolized, they become secondary molecules or secondary chemicals called metabolites. And there are two types of metabolites. There are active metabolites and inactive metabolites. Now, inactive metabolites don't have any effects. They have no drug effects. And because they're less lipid soluble and they're not going to bind to active sites, they basically remain in the water of the body and are excreted via urine or sweat. And other metabolites are active, which basically means that they do bind to active sites. They are bioavailable. They're still less lipid soluble than the original molecule, but if they're lipophilic enough, they'll return to the bloodstream from the liver and have their own actions on those active sites. Those actions can be similar to the original molecule, but usually they're different. So we can look at some examples here of active and inactive metabolites. So, for example, aspirin is hydrolyzed into an active metabolite. So aspirin isn't really what necessarily has the non-steroidal anti-inflammatory effect. It's the salicylic acid. And then salicylic acid is then glucuronidated. It's a big word, but it's basically metabolized into salicylic glucuronide, which is an inactive metabolite. So I've bolded the active metabolites. Similarly, with heroin, heroin is hydrolyzed into 6-acetylmorphine, which is hydrolyzed into morphine. And as we know, morphine is the pain-killing, the active pain-killing metabolite of heroin. So heroin itself doesn't bind to any receptors. It's the morphine that it gets metabolized into that has the effect. And then morphine is deactivated by glucuronidation into something else. This is just to sort of illustrate the difference between inactive and active metabolites, and it's these inactive metabolites that ultimately end up in the urine. So when we're talking about drug testing, they're not necessarily testing for heroin. They'd be testing for this M3M, this inactive metabolite that gets excreted in the urine. So I'm going to insert a question here about phase 1 and phase 2 metabolism. So most degradation occurs in the liver by enzymes that metabolize a variety of molecules. And one of the primary liver enzymes is a class called cytochrome P450 or CYP450. And this is a class of enzymes. So there are many different specific forms of cytochrome P450. And this class of enzymes is responsible for the majority of drug metabolism that occurs in the body. And something to consider when we're talking about pharmacokinetics is that some drugs actually are able to alter the activity of CYP450. So if you remember in class, we talked about how drugs can affect one another's depot binding, which ultimately affects its pharmacokinetics. Well, some drugs can alter the effect of enzymes, which also alters pharmacokinetics. So one example that's really interesting is the relationship between nicotine and schizophrenia. So as you can see here, we're looking at psychiatric diagnoses and the prevalence of individuals with those psychiatric diagnoses who use tobacco. And as you can see, people with schizophrenia, I mean, this is a pretty large proportion of these individuals use tobacco. So interestingly, nicotine actually inhibits some of the CYP450 enzymes that are known to degrade antipsychotic medications. So there's sort of a self-medication that's going on here. People with schizophrenia smoke cigarettes to inhibit the enzymes that are breaking down chemicals that they need to basically inhibit the symptoms of their schizophrenia. So it's good to remember that pharmacokinetics of one drug can be altered by other compounds that influence degradation. So CYP450, cytochrome P450, contributes to what's called first-pass metabolism. Again, this is another key word. And first-pass metabolism occurs with oral administration. So a medication is taken orally, it passes through the stomach, goes into the intestine, and then is transported via this portal vein into the liver. And once it's in the liver, it becomes subject to a number of enzymes, including cytochrome P450. Now obviously, first-pass metabolism can be bypassed through other routes of administration that don't pass through the intestinal tract. And certain drugs are very sensitive to this first-pass metabolism, meaning that they're highly degraded by cytochrome P450. And this is one reason why oral administration results in very low bioavailability. Not only are drugs, degraded by the strong stomach acid in the gut, but they're also sent directly to the liver, where they're degraded by these enzymes. So one example of drugs that are highly metabolized by liver enzymes would be heroin. Heroin, and morphine for that matter, strongly degrade in the liver. So when it finally gets into the blood, so it goes into the liver and travels out through the hepatic vein into the circulation. When it finally gets into circulation, there's much less of the drug available, which is why heroin is most often administered in other ways. So I'm going to insert another question here. So in the body, all chemicals have a constant rate at which they're degraded, their own constant rate. And this is called a half-life. So a half-life is pretty self-explanatory. It's the amount of time it takes for 50% of available drug to be cleared. So if you look at this figure here, we're looking at the concentration of drug in plasma, and these are units of time. And so here we have the drug at time point 0. So this is the maximum plasma availability. And it takes one half-life to reduce that to 50%. So this is sort of like 100%, now we're down to 50%, and it takes one half-life. From that point here, it takes one more half-life to degrade the drug down to 50% again, one more half-life to bring it down to 50%, one more half-life to bring it down to 50% of that. And this degradation pattern is called first-order kinetics. Let me insert another question. So in general, it takes about 4 half-lives to mostly eliminate a drug. And so you can generally multiply a drug half-life, whatever it is, by 4 to know how long before it's eliminated. But remember that like the half-life of heroin, remember that the half-life doesn't necessarily give you the whole story, right? So take heroin, for example. You could look at the half-life of heroin to know how long it takes for it to be eliminated from the body. but the active metabolite is morphine. So you're not only looking at how fast heroin is cleared from the body, but how fast that morphine is cleared as well. And while half-life is a general rule of thumb, there are other factors that influence the rate at which a drug is eliminated from the body. So we already mentioned that some chemicals can inhibit or increase the activity of liver enzymes that break down a drug. And we talked in class about how ascorbic acid in orange juice can inhibit monoamine oxidase. But there are also individual differences, mostly genetic, in enzyme capabilities that affect drug clearance. And so one of the classic examples is Asian populations and acetaldehyde dehydrogenase. So Asian people from Asian populations have slower acetaldehyde dehydrogenase. It's just a genetic thing. Basically, the acetaldehyde isn't broken down as quickly or as completely. And acetaldehyde is sort of basically what causes you to have hangovers. It's a crummy thing to have in your body. And generally, when you have increased levels of acetaldehyde, you experience flushing, headache, nausea, basically not a lot of fun. And so naturally, if every time you drink, this is what happens, you don't really drink that much, which is why reduced alcoholism is observed in Asian populations. So it's important to, in addition to keeping in mind drug-drug interactions, to also keep in mind that genetic predispositions also play a big role in how enzymes process drugs. And that's it. So here are the terms that we went over in this lecture, terms for your class notebook. Again, use your textbook, use the internet, figure out how to make these terms make sense to you. And if you have any questions, be sure to write them down and we can address them in class. And so that's it.